what we did last time was to look at half-life specifically, for which I gave you a formula to specifically put for half-life questions. Today we're going to look at not necessarily questions about half-life, but just exponential growth or decay. Generally, these problems are worded in a way of decay because we talk about a certain drug, for example, that you take, and then after a certain amount of time, uh, less of that drug remains in your system, right? That's how drugs work. You take them, your body processes the drug, and after about, like, for this example, you take 125 milligram of a drug, and after an hour, only 87.5 of the milligram, 87.5 milligram of that drug remains in your body. So generally, they are decay questions because it is usually a drug question or a bacteria. I guess bacteria questions would be growth because you have a certain amount of bacteria present in a culture, and then after a certain amount of time, that bacteria number increases because the bacteria is populating. So we have examples of both growth and decay. Now, these are going to be exponential models, which means our kind of standard exponential equation is y equals a times b to the x power. This is from earlier in the chapter. We know what an exponential function looks like, and it has these parts, so we'll label these parts as um, b is the thing that is the factor of growth or decay. A is generally the initial amount, and x is going to be time in these specific exponential models. And then y will be the final amount. Now, we're not going to use x, y for these functions because they're going to tell us which variables to use. So if you look at this example, it says write an exponential model, which means we're going to write an equation that looks like this, representing the amount of drug, which is going to be D, remaining in the patient's system after T hours. So let me go over this first example with you using this type of exponential model. So writing the model with the variables given in the question, what I would write is I would say something like D is going to be my final amount left in the patient's system, would be modeled by some kind of starting amount. We'll call that D sub 0 for the amount of drugs in the system at time 0, times some factor of decay, which I'll leave as b from the original equation. And then instead of the exponent being x, I will put t because it's going to be time. All right, so generally, you can leave it as y equals ab to the x, but it makes more sense to switch to the variables that they give you so that the amounts and the time are easier to input into your formula. Or if someone were to ask you to write an equation relating these variables, you're going to need to write your answer using these variables, so you may as well start with those variables to begin with. So we can actually start filling in things that we know. Actually, we don't even need the D sub naught here. Let me erase this. Because the initial amount of the drug remaining in the patient's system is fixed and it's given in the question, a doctor prescribes 125 milligrams of a drug, that means our starting amount is 125. So we can actually fill that in because we're not going to be doing any other starting amounts for this question. We may do different times and then we'll have different resulting final amounts, but the starting amount is fixed. The thing we need to find here is the factor of growth or decay. In this case, it's going to be a factor of decay. So the this 1 hour 87.5 milligrams given to us in the question here is a 1 comma 87.5 as kind of a t comma, give me 1 second, let me write this down here. This point given to us here is actually a t comma d point. So we can use that point to find this value b. So let's plug that in to our original formula. So d is 87.5. There's 87.5 milligrams remaining after an hour. Our starting amount is 125 times b to the first power. Right, and now we can solve b. This is just an algebraic, we divide by 125. So b will equal 87.5 divided by 125. Right, and as far as the homework on XYZ is concerned, you probably have to use a calculator to divide that and get a decimal for b. So I will give you the answer for both homework, how you would answer the homework question, and how you would write your answer on the exam. 87.5 divided by 125 is 0.7. So b is equal to 87.5 divided by 125, which is, exactly 0.7. So when I write my answer here, I would say d is 125 times 0.7 to the t power. That would be the equation for XYZ, for the XYZ homework assignment. If you don't have a calculator, you can just replace the 0.7 with an 87 over 125. You can just put that in there for your answer and leave it as that. So on exam, you would say d is equal to 125 times 87.5 divided by 125 to the t power. Okay, part B says determine the half-life of the drug. Half-life generally refers to a amount of time. It's specifically the amount of time it takes for half of a substance to decay. It's the amount of time it takes for half of the substance to decay, and so after half of the substance has decayed, only half of the substance would remain. Meaning, if I'm starting with 125 milligrams of a drug, then after one half-life has passed, there would be half of 125 milligrams left. So that's going to be 62.5, but in general, I'm going to show you that you don't really necessarily need to know exactly what half of this number is, because let me just write down 62.5, and then 125 times 0.7 to the t power. That was our original answer from part A. That is how this drug behaves. We plug in an amount of time, and we find out how much of the drug is left in the system. So if I want to know how much time it takes for half of the drug to remain, we want half of the drug remaining as our D. And now the reason why you don't really have to know what 62.5 is, or you don't have to know what half of 125 is we're going to divide by 125 to begin, and always end up with a 1/2 is equal to the factor of decay to the t power. You're always going to end up, when you're trying to find the half-life of a drug, you're always going to end up with a 1/2 equals essentially the b to the x part of the formula. So you can kind of skip this. You can kind of skip this step and go straight to 1/2 equals the b to the x part of the equation. How do we solve for t for something like this? How do I solve for t? How do I get t by itself?
Do you take the log of both sides?
Yeah, that was exactly what we did this whole chapter, essentially, right? How to solve these types of exponential equations. We're going to need to take the log of both sides. It doesn't matter which log we take. When I say which log, I'm talking about the base of the log. I'm just going to use natural log because it's shorter to write. It's just an ln of 1/2 equals ln of 0.7 to the t power. And the purpose for doing that is we can take this t and we can bring it to the front, right? That's our power rule. So ln of 1/2 equals t times ln of 0.7. And then I can divide both sides by that ln of 0.7. So t ends up equaling ln of 1/2 divided by ln of 0.7. And we can leave it like that as far as the exam is concerned. But for homework's sake, it's going to ask you probably to round this half-life to the nearest, actually don't know, nearest hour maybe, nearest minutes maybe, or like 2 decimal places of an hour, something like that. So in that case, we would need to plug this into a calculator. Ln of 1/2 divided by ln of 0.7 gives me 1.94 approximately. And this was in terms of hours because our time in the original equation is in terms of hours. Right, but this would be on exam. Sorry, you still need to include the word hours in your answer, but this would be how you leave the number on the exam. Or I guess instead of 0.7, you would have the 87.5 divided by 125, but you would leave the answer in terms of the natural logs and the fractions. Any questions on how to do model using an exponential growth or decay function, y equals a times b to the x? Okay. Another form of a exponential model would be to write an exponential growth model with a base of e. Instead of having b to the x, we're going to have that b represented by an e to the r. This is the formula you use to figure out what r is, because e is already a number, right? There's nothing to figure out with the e. So the only thing you need to figure out is the r, which is just equal to the natural log of b. So then we rewrite a function like this. This is written as y equals a times b to the x power, and we want to convert this to write it as a continuous exponential function, which means we want to write it as y equals a times e to the r to the x power. So we're replacing that b with an e to the r power, and r is going to be just natural log of b. So if I know what b is, which I do, right? B is equal to 3.1 here. So we can find r, which is just natural log of b, which is natural log of 3.1, which is, on a calculator, 3.1 natural log is approximately, actually I'm going to leave it as natural log because we don't want to round probably at this point. Natural log of 3.1, so we're going to take that and we're going to put it where the r is, right? So y will equal, the a is the same from the original question, so 2.5. But instead of b, we're going to write e to the natural log of b, or e to the r, which is e to the ln of 3.1 raised to the x power. So we'll write our answer as such. So converting is not super difficult. You take the b, you find natural log of b, and that's the r in this formula. And then we can, I guess we can simplify slightly. Since we just multiply r times x in the exponent, we can say this is 2.5 times e to the x times natural log of 3.1. All right, we multiply r times x. If the homework, I haven't looked at the homework, but if the homework asks you to round r to a certain number of decimal places, then you would obviously do that instead of leaving it as natural log of 3.1. Let me see what it says real quick. Yeah, it does ask you to round this natural log of 3.1. It will ask you to round it to like 4 decimal places. So make sure you do that when you're doing the homework. You use a calculator to find an approximate value for r. Okay, that concludes chapter 7. Are there any questions on this last part before we move on to chapter 8? All right. Chapter 8 is going to be all about sequences and series. 8.1 is just going to be about notation, and then we'll talk about specific types of sequences. And then finally, we'll talk about series, which is essentially a sum of all of the terms of a sequence. So what we're talking about with sequences is just a kind of a set of numbers with some kind of pattern to them, right? So the first thing we're going to be concerned with is writing an explicit formula for a sequence, which kind of relates the term number of a number in the sequence with the actual value of the number in the sequence, right? So when we talk about notation, we label the terms as a sub n, or sorry, a sub n is labeled for the nth term, but if I'm talking about the first term of the sequence, we would label that as a sub 1, which has a value of 2, so that's the first term in the sequence. A sub 2 will have a value of 4 because that's the second term in the sequence, and the third term is a sub 3, and so on. Right? So if I have a sequence like this, this is a sub 1, a sub 2, a sub 3, and so on. Right? So the first term is a sub 1, which is equal to 2, a sub 2 is equal to 4, and so on. Determine the nth term for the sequence given here. This is going to be essentially pattern recognition as far as the first section of Chapter 8 goes. Easiest way to kind of analyze and find a pattern, because the pattern is not going to be, if you want to find a formula for the nth term, we're not looking for a pattern from one term to the next, but rather a relationship between n and the value of the term. So we're looking for a pattern, or we're looking for a relationship between n and a sub n, meaning the first term, second term, third term, fourth term, fifth term as my n needs to translate to 2 for 8, 16, and 32. We're looking for a relationship between these two numbers, right? I need to be able to plug in 1 into an equation and get 2 as my output. I need to be able to plug in 3 and get 8 as my output, and so on. So while the pattern from one term to the next is kind of helpful in finding that equation, we're more so worried about going from n, from the input, to the output, which is going to be the values of the terms. So a sub n will be some kind of formula that has an input that's n and an output that is the value of the actual terms in the sequence. So if I were to plug in, if I wanted to go dot dot dot, and I wanted to find the 13th term of the sequence, I don't have to find all of the terms before it. I can just plug in 13 into an equation and get this value for the 13th term, right? So what is the relationship between n and the nth term? The number, the index, and the term in the sequence. What is the relationship there? Can you guys tell?
Is it 2 to the power of n?
Good. 2 to the power of n does seem to fit all of these, right? If I take 2 to the first power, that's 2. 2 to the second power is 4. 2 to the third power is 8. 2 to the fourth power is 16. And 2 to the fifth power is 32, which means that is going to be our nth term explicit formula, which means input is n, output is directly the nth term, right? If I wanted to find the 13th term, that's just 2 to the 13th power, right? So there is kind of a relationship between this formula we found and the pattern of going from one term to the next. Because if you pay attention to that pattern, we're multiplying by 2 every time, right? So this 2 actually shows up in both places, but that multiplying by 2 every time by itself is not enough to write this, to write the explicit formula for the sequence. In this case, it was because we started at 2, but if the sequence started at a different number, we actually have to modify this so that our terms start at a different value. So this is the explicit formula for this sequence that was given to us, the 2, 4, 8, 16, 32. And actually it's also down here. If you look down at the bottom of the page, it gives you the explicit formula for the nth term. And the way it's written up here, this with the dot 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 at the end is an infinite sequence. But down here we talk about a finite sequence which would have a stopping point. Right, so this is an example of a finite sequence. So if you stop the sequence at any term, then it becomes a finite sequence, meaning it has a finite number of terms. A nice way of representing these sequences is to graph them. Now, when you graph a sequence of numbers with their corresponding index value, you get individual points, discrete points on a graph. You don't necessarily get a curve because we don't have any numbers in between these, right? We're not concerned with like the 1.7th term in this sequence. We're always concerned with whole numbers or counting numbers, 1, 2, 3. So the first term, second term, third term, which means these are going to be discrete points. Now they are following a curve that we've seen before, this kind of curve that we don't draw because we're concerned with a sequence here, but they're following an exponential growth curve because this function that we wrote, 2 to the n, is an exponential growth equation, right? So because this is exponential, this is representing exponential growth, these dots are following an exponential growth pattern, right? They are on a curve that is exponentially growing. And the curve that they're on is the 2 to the x curve, y equals 2 to the x curve. Cool. Sequence, there's some terminology here. A sequence is just a list of numbers. We use indices 1, 2, 3, 4, 5, 6 all the way to n to represent the nth term in the sequence. And the explicit formula defines the nth term related to the index of the nth term, which would be n. If a question asks you to write the first 5 terms, you just write the first 5 terms. You can either write it as kind of a sub 1 equals whatever, and to find a sub 1, I'm replacing my subscript of n with a 1, which is kind of just like plugging in 1 into this equation for n, right? So to find a sub 1, we plug in 1 into our formula. So negative 1 to the 1 power times 1 squared divided by 1 plus 1. And that ends up being a negative 1 on top and a 2 on the bottom. So we get negative 1/2. Right, a sub 2 will equal a 2 plugged in for n, so negative 1 squared times 2 squared divided by 2 plus 1. And that is a positive 4 divided by 3, so 4/3. And so on. So we can plug in for a sub 3. I guess I might as well finish this question. Negative 1 cubed, 3 squared divided by 3 plus 1. Negative 1 cubed is negative 1. 3 squared is 9. So we get negative 9 over 4. A sub 4 would be negative 1 to the 4th. 4 squared, and then a 4 plus 1 on the bottom. 4 squared is 16 divided by 5. And then the 5th term, which you may have started recognizing a pattern in these already. First of all, we're alternating between negative and positive. And there's a different pattern for the numerator and a different pattern for the denominators, because we kind of have 2 formulas here. We have a formula for the numerator and a formula for the denominator. So a sub 5, I think, is going to be negative 25 over 6, but we'll check that by plugging in 5. Negative 1 to the 5th times 5 squared divided by 5 plus 1. which is a negative 25 divided by 6. So then write the first 5 terms. I would write the first 5 terms as negative 1/2, comma 4/3, comma negative 9/4, 16/5, and negative 25/6. That is the final answer for the first 5 terms of the sequence. Okay, so that's how we write. That's how we find the terms of a sequence if we're given an explicit formula, right? We just plug in n. If the question asked instead of the first 5 terms, it asks for like just one term, like the 8th term, for example, you would just plug in 8 for n, right? So then you would find a sub 8, and that represents the 8th term in the sequence. Cool. Next, we're going to write explicit formulas for a sequence given the terms. In the examples where you have fractions, just like we saw in this example back here, I pointed out that there was some kind of pattern for the numerators and a separate pattern for the denominators. And remember that came from the formula having a kind of an explicit formula in the numerator and an explicit formula in the denominator. So when you see a fraction, a sequence of fractions, it might be a good idea to kind of look at the numerator and denominator as kind of 2 separate sequences, right? We have a sequence that goes 2, 3, 4, and so on, and then a denominator sequence that goes 11, 13, 15, and so on. So let's see if we can write a explicit formula for the nth term in each sequence given here. So just from the first 3 terms in the sequence, we want to find a relationship between n and the numerator and n and the denominator separately. So maybe I'll make a little table like I did before. I'm actually going to make a double tiered table here where I have n, which goes 1, 2, 3, and so on, and we only have the first 3 terms. So I'm going to focus on the first 3 terms here, and then my numerator and my denominator as 2 separate numbers. So my numerator sequence goes, let's just attach the negative to the numerator because some of the terms are negative. So my numerators go, let's ignore the negative. I'll explain how the negative, positive, flipping back and forth between negative and positive works after we do this. Let's just focus on the numbers. So my numerators are going 2, 3, 4, and so on. My denominators are going 11, 13, 15, and so on. So if I want to write a relationship between the nth term and the numerator and the denominator separately, can you find a way to get from these values, the 1, 2, 3, to the 2, 3, and 4? How do I get from n to the numerator? What's the formula for that jump? Or what's the explicit formula for the numerator? So ignore these for now. You're just looking for a formula in terms of n that gets you from 1 to 2, from 2 to 3, from 3 to 4, and so on.
N plus 1.
Good. N plus 1. And I see it in the chat as well. N plus 1 gets us from n to the numerator, right? So that means my numerator in my explicit formula is going to have an n plus 1. Just like we did on the in this example that we did earlier, that n plus 1 made our denominators go 2, 3, 4, 5, 6. Right? We see the same thing happen here with our numerators. 2, 3, 4. I guess we're going all the way to 8. But that is going to be my numerator expression. What about the denominator? This one's a little bit harder. How do I get from, so ignoring these numbers, how does 1 become 11, 2 become 13, and 3 become 15? We need a formula for that. This one is not as easy.
Would the denominator be 9 plus 2n?
Good. 9 plus 2n does work here. I'm going to write it as 2n plus 9, just so I have the kind of the y equals mx plus b formula there. Essentially, what we recognize about the denominator is that we're counting by twos. If we look at this kind of increase between one term to the next, we're counting by twos, which means we have you can think of it as having a slope of 2, right? As the n goes up 1, the denominator value goes up by 2, which means we have a 2-to-1 ratio, which means we have a slope of 1. If you want to relate this back to kind of y equals mx plus b, this is essentially an equation of a line, right? This is y equals mx plus b. And so because we're increasing by 2 every time, my slope is going to be 2, and then you just have to find this extra value, the plus b that's added to it, to make these true, right? 1 needs to end up being 11, 2 needs to end up being 13. So once I know that I'm going to do 2n, I just need to find this plus value at the end. So whenever you have a sequence, so this would work for the first sequence as well, right? Because these are increasing by 1 every time, which means my slope is going to be 1 for this linear growth, right? So if you have a pattern where you're adding the same number over and over again in a sequence, that is a linear sequence. These points are going to lie along a straight line, right? And the slope of that line would be how much you're increasing every time. So we get a 2n plus 9 here. Now I told you how we were going to deal with this alternating negative, positive situation, and that's done the same way that it was in this example that we did on the last page, where we had a negative 1 to the n. That's what was causing the negative, positive, negative transition from one term to the next, because as you plug in, as you change the exponent on the negative 1, it switches from an odd exponent to an even exponent to an odd exponent to an even exponent, and so on, changing the value of negative 1 to the n to be either negative 1 or positive 1, depending on whether we have an even or odd exponent. So how we represent a alternating positive, negative sequence is just chuck in a negative 1 to the n at the beginning of the sequence, or at the beginning of the explicit formula. So the explicit formula here, a sub n, will be a negative 1 to the n, so that we can have that alternating negative positive situation. And then we can use our numerator and denominator to make a fraction here and say my numerator is n plus 1 and my denominator is 2n plus 9. So this will be a times, and that is the explicit formula for that sequence. As far as 8.1 is concerned, there is no like nice formula or algorithm for getting to this formula, because it's kind of just you can write a sequence that has fractions, you can write one that alternates between negative and positive, you can write one that is just whole numbers. So it's kind of a just pattern recognition and reacting to whether this is a linear sequence or maybe you realize it's an exponential sequence. So I guess some hints as to what kind of formula you would write for n is, I don't know how to write this, but if the numbers are increasing by a certain amount, so if the pattern is, I guess we can say the pattern is a plus 2 pattern, or if it's a plus something, plus number pattern from one term to the next, that means that this is a linear pattern, a linear sequence. I'll call it a linear pattern. I don't want to call it, that's not a technical term. We have a linear pattern here with slope equal to 2. If, on the other hand, you're multiplying by something from one term to the next, and we saw an example of that earlier in this type of example where we had 2, 4, 8, 16, 32. So here we have a times 2 pattern from one term to the next. Oops. And if you have a multiplication pattern, then you have a exponential pattern. Meaning you're going to have that number that you're multiplying from one term to the next raised to some kind of exponent that has an n in it. That's why we ended up with an exponential function for that type of pattern. So that's something to look out for when you're looking to find this pattern from, or not this pattern, but the explicit formula for a sequence. So when you're doing these, like this one, for example, I think the denominator is following a multiplication pattern. Like the 25 to 125 is a times 5, and then this is also a times 5. So you're going to have some type of 5 to some power in your explicit formula when you're doing that one. This one also may be like that. It seems like you're multiplying by something. The reason why I think that is because the numbers are growing so fast, so there's got to be some kind of multiplication going on from one term to the next. So you do kind of consider what's happening from one term to the next, but when you're writing this formula, it has to be a formula that gets you from an n value to the term that you want, right? Sorry, we actually didn't finish this question. We wrote the explicit formula. The question also asks us to determine the number of terms in the sequence. So the number of terms in the sequence in this case is pretty easy to find, but in other cases we may have to just set this term equal to this explicit formula and solve for n, which would find what number term it is. But in this case, because the numerators are going 2, 3, 4, we can just use the numerator to find that. I know that this numerator 8 must be a result of this n plus 1, right? So I know that 8 has to equal n plus 1 in that last term. So n must be 7. So there are 7 terms in the sequence. So you can use part of the formula with its corresponding part in the term to figure out. You can also do the same thing with the 2n plus 9 and the 23. If I were to set 23 equal to 2n plus 9, we should still get 7 terms, right? If I subtract 9 from both sides, this is a 14 equals 2n, and n equals 7. So either way, we find that there are 7 terms. Right, and that is what we're doing in 8.1.